Okay, I'm going very fast. First of how we solve the question. Don't worry about the numbers, but try to observe the general steps, how we solve. So if you look at the question, you know that this is chapter 7 question. You look at the question, you see spring, you see force, you see angle, you see moment, and you're given P is always perpendicular to the end of the path. Also, the spring have unstretched length, remain vertical position due to roller gap at P. Okay, so have unstretched length 0.5 and remain in vertical position due to roller gap. So this one always stay at roller gap, but they have an unstretched length of 0.5. So this one will stretch as you pull it longer and longer. Determine the total work done by the force. He asks you to find work. What is work? Work is force multiplied by distance traveled. Okay. So if as long as you have a force, force and moment. Now you're in chapter 7 already. So when you talk about work, you need to consider force and moment. Moment, how you find work? Moment multiplied by the distance, by the angle rotate by the moment. Okay. Work is distance. Force by all forces acting on the bar when it's rotated downwards from 0 degree to 90 degree. So 0 degree means this one here. So in this one here is 0.75. The spring initially is 0.5. When 0 degree, the spring is stretched. The spring already charged up some energy there before it starts. When this one over here, this one 0.75, we tell you already, before it starts, the spring original length is 0.5. It was stretched 0.25 meter. Okay. Then 0 to 90. 0 to 90, you need to consider the length at 90 degree. This one you pull here. Here to here is 2 meter. So when here means here to here is 2 meter, 90 degree is here. So 2 meter plus 0.75. You need to know how much is stretched at 90 degree. Yeah. So basically, you are given some mass over there. The bar has a mass. Okay. So these are questions, but especially chapter 6 or chapter 7. Go to your free body diagram. Put in the G point. Straight away go to G point. You label G and then you draw a weight pulling down. Because weight also doing work. So normally students will forget lah. When it comes to 6 or 7, they forget weight actually create work. Because it's not written in the diagram. Okay, you draw free body diagram. Pin, I already explained in the previous lecture. Pin, you have two forces up and to the left or right. It doesn't matter. You want to draw this red arrow to the right also can. But in this case, I just draw to the left. Right? In this case, this you draw to the left. You answer later, you find AX is negative, means this one originally should be to the another direction. Okay. So you draw free body diagram. There's a pin, there's a force there. Two forces are. Okay. Then the spring forces, the P forces, and this will be the one that careless mistakes always happen. As you go deeper, you forget your number. This is a careless mistake usually. You forget your W. W at where? At central of the rock. Then there is an M given. Theta. and the length in that. Now, as you move into chapter 6 and 7, your free body diagram will be moment, force and moment. Particle don't have moment because you see as a whole big body. Moment happen inside, you cannot see. Okay, then you put in all the parameter, all the distance, so on. Then you start to look for displacement already. Means you do work analysis. So omega, which is not omega, W equal to distance traveled before and after. So the wave, how much is travel from 0 degree to 90 degree? How much is travel? How much travel? Can you imagine? We're now focusing on doubling. This is the question. This is a G. This is a W. What is the distance from P to W? The distance. What is this distance? 1.5, 1.5. Who don't understand why is 1.5? Who don't understand? Okay. So your W actually moving from 0 degree to 90 degree. So you are moving 1.5. Okay. Unit for work again is joule or Newton meter. Okay. You should be able to understand why this one positive. Why weight is positive. Why in this case is positive and not negative. Because you are assuming all your distance go down to positive. You see all the work here, you assume your y is positive. Then the moment actually moving in the 90 degree. You see the step here, we're actually using radian. Okay. So again, this work for moment. This one is not degree. This one just put a mark in your revision note there. This one is radian. So you put your work done by moment is a radian, right? Get something. Spring also. Spring. You have one spring there. You take the distance before and after, right? It was stretched 0.52 meter before it starts 0 degree. 90 degree was stretched 2.25 meter. So I did show you the after 90 degree, what is the total length of the spring? Right? You substitute inside this spring equation, you get negative work. Then you have 3 work there. P force, again, this one swing in rotational, right? It's P 90 degree. It swing from 0 to 90 degree. What do you see? It's circular. It's actually quarter of pi. Not quarter pi, but quarter circle. Okay. So 2 pi equal to 360. Pi equal to 180. Half pi equal to 90. This is radian. So you know distance traveled. So the distance is 4 point something. Okay. Because y, this is r, this is theta, this is s. What is the s? Equal to r theta. Okay, your theta is half pi. Your r is here. R in this case is 3 of the length. Okay. In reaction, they do not displace. They are staying at their position. So no work done by the two pin there. By the pin force is no work there. Okay. So you find total work. Okay. You add work, W, moment, P. This one do not do work. And you add up, you get one answer there. Another one is principle of energy, work and energy. So again, because you have motion, then you have kinetic motion. Okay. Principle of work and energy, you will consider kinetic in this case first. Later, we will consider potential. Okay. This one is just show you that we are considering kinetic energy first for a body. You see this equation before, particles, but now we're considering the kinetic energy for each body. And I write on the whiteboard here, again, it depends on the motion. Okay, so kinetic energy for each body, we have mass effect, gravity, mass, central mass effect, and inertial effect. So it's always good you look the question from the center of mass, so you can cancel out the gravity, center of mass effect. So if you're doing translation, you do the first one, P equal to half mv squared, and Y in particles, you always use this one because your particle always moves in the straight line or curvature line. So then if it's rotate, it's a angular motion, you use half I omega squared. Okay. And if it's a combination between translation and rotation, or then you use general plane equation, half IC omega squared. Or you use the full equation. Okay. Now let's look at this equation, this question. So you have a pin, round body tied to the spring. Spring coefficient is given. There's a spring. There are two pin here, all right. Radius given, moment given. So again, rigid body, you need to consider moment and force. Force multiply, how to find work? Work, as long as there's a force and there's a displacement, it gives you work, and moment will consider the radian, the distance traveled by the rotation. Okay, so given mass of the body of the disc, determine angle which it must be rotate to attain angular velocity 2 radian per second starting from rest. Means you need to find what is the crank angle, what is the angle you need to turn so that when you release, the disc can rotate at 2 radian per second. Okay, so this equation, these slides will show you the application in machine design. Sometimes you need to design something that you need to load the spring and then launch the vehicles or launch the devices. Okay, this one is more in the industry application. When you want to design something, you need to turn the thing a certain angle, then charge up the spring and do the operation. The act upon the constant couple moment, even this one, right? Spring original unstretched and the cord right around the rim of the piece. Okay, so this one a bit tricky because this one, when this one turn, this one will change angular into distance traveled. Okay, so I'll go very fast this example. First, you draw free body diagram. You're focusing on the disc. So this alone, you go to the center of gravity. In this case, O. You can write G, but remember you have two body there. So you write G. Then the first thing you write is your weight. Then because it's tied to the pin always have two component, X and Y forces. Okay. Then there's a moment from the question, and the thing I asked you to rotate, right, to charge up the spring. So what is the force that you should draw at this here? Does this go up or go down? Go down, 1. Okay. Spring. Go down. Down, huh? So you just imagine you are this object, then you rotate, what do you feel on the hand? What do you feel? Right? So go down, spring. So some of you might still confuse on why this one go down, not going down. If you don't understand this one, go home and think. Try to imagine you are this, and you try to turn this one, what your hand feel. Your hand feel go up or go outside or go inside. Okay, so you use the principle of energy and work. So left hand side is before, right hand side is after. So you substitute all the value. So before it start, no kinetic energy. There's nothing happen, right? So T10. In the test 2 or final exam, please write this one. Don't assume I know you know. You don't write, then you know mark. Okay? Or you want the fast way, you write this one, you draw arrow, also I give you mark. You draw arrow, you write 0 here. Also I give you marks. Just don't empty out. You empty out, I assume you don't know. Okay? And then at the next step, you suddenly this one missing. Then I'll put a question mark. Why T1 missing? Okay? I don't assume things. I see what you write there, I give you marks. T2, for the disk, we use I omega squared. Why? Because this one rotates in angular motion. This one do not move to the left or right. So we don't use this one. We use this one. Yeah. So I hope you see the application here. So you apply. How to find this one? Refer to table. How to find mr squared? This one refer to table. You're looking at this point. So you're using ZZ. On the table, you have Z and Z comma. Z comma is where? Here. You're looking at here. You're looking at the center. So that's why your IO is half mr squared. This one. You're looking from here. Okay. Here you apply. Then you substitute value, you get the P2 for the kinetic energy. Okay, this one is after, before and after. Before and after. Then you find the work. Okay, now to do work, you know that P doesn't do work. In your answer, please write, in your answer, in the assessment, test 2 or final exam, please write in forces X, forces Y, do not do work. Please write this statement. This got 1 mark. At least 1 mark there. 1 or 2 marks. You don't write means no marks. Okay. It's a free mark. This one is a bonus mark. You don't write, then no mark. Okay, this statement. If in here, you must write on the work. Pin do not do work. Force on the pin X, OX, OY do not do work. This one costs you 1 mark, 1 to 2 marks. Then you consider moment. Moment, again, work done by moment is moment multiplied by the angle it rotates. So this one, it rotates 2 radian. Okay, 2 radian per second. But this one is with angular velocity. We don't know the angle. We want to find the angle. The question asks us to find the angle. So this will be the missing parameter. But it's in radian. Just be careful on the radian. Okay, spring also same. Same equation. Okay, so S1, you do not stretch it, so 0, cancel. you only need to find displacement for the final condition. So you have angle and S2 here. Okay. So you have moment, do work, spring, do works, W do work or not? Do not do work because it doesn't move. Okay. If this one fall down, yes. F also, this one spring do work, right? So you need to convert your K is given. You need to convert your S in terms of angle. Again, S is what? S is R theta in the quadrant. Right? S equal to R theta. So convert your S equal to R theta. What is R? Is 2.2. Theta, you don't know. Substitute only one unknown inside this equation. Right? You know that this is a general equation, principle of work and energy. You continue to expand inside this equation, only one unknown, really theta. Here theta, and you have all the value. Press calculator, solve it. Again, it is in radian. Your answer, you need to put in theta. If the question asks you angle, please put the answer in degree, not radian. Because we assume you are communicating with an operator, with someone with this low level in education. You tell him, hey, please rotate 0.24 radian. He'll look at you like, don't know what you're saying. You must communicate in a way where all the non-engineering people, they know what you're talking. Okay. All right. Another one. You see the question. There is a G value there, and you're given gyration. Again, fixed already. You see gyration is mk squared. The equation for I is mk squared. So given mg, how we rotate, moment is given. Spring is given here. Roll from rest without slipping. Meaning what? In your free body diagram, we expect you to put in friction force and normal force in free body diagram. But friction force, normal force do not generate work. You must write that one. Fs, F friction, and normal force do not generate work. That one costs you 1 to 2 marks. If you don't write, then no mark I can give you. Right? They give you the center of mass G move certain distance. Stiffness is given so and so. So what is the normal procedure for chapter 7 when you want to use the principle of work and energy? Okay, you draw free body diagram. On the left, you focus on force and moment. Right? So here, center of mass, straight away, draw W. Go to the center of mass, draw W, mg. You write capital W equal to G. Then you put in the moment. There's a contact force, friction force. Right, so this one you rotate what clockwise, subject to a clockwise coupled moment. It turn this way. Turn this way. Where is the friction force? You rotate this way. This way. This way. You go against the motion. Okay, it's like rotating like this. So yeah, the motion, you will stop the motion. So motion go this way. I mean this surface go this way. So the friction goes this way. Okay. So you draw the spring. Spring is when you rotate clockwise like that, you'll feel that your arm is stretching out. If your is round body, you rotate this way, you'll feel your arm is stretching out. So your force is pointing to the left. And remember, friction force and contact force. In this case, in point B, I just label as kinetic diagram again. Kinetic diagram, we focus on the motion, right? So here we focus on omega, okay, and velocity of the center of gravity, which is velocity, okay, at the center of mass and omega. Is a bit different from the rigid body. Rigid body, you don't see omega and v in at this location. In particle, you see your v is outside the kinetic. Okay. Okay. So in chapter 7, chapter 6 and chapter 7, please put your v and omega near to the bottom. Okay, so you have I and IC. Why I use IC? Because that is the most easiest way to find omega. Just put your ruler there. And you know that this one always, round body always move to one direction, either left or right. So you just draw perpendicular direction. Move your ruler over here. Draw IC point. IC actually is your radius. So V equal to what? V equal to omega R. Rearrange the equation, you find your omega R. So you find the kinetic force first. Kinetic first doesn't move, so 0. Again, if you're lazy, you just draw an arrow here. Draw an arrow, 0. Right, draw arrow, right, 0. So what happened at the end of the process? There's a rotation. So we'll use rotation. T equal to half I omega squared. So you can use the long one or you can use the short one. Okay, you either use the long one or the short one, or this one, IC omega squared. Or you can use MK squared plus MR squared. Okay. So this is IO equal to IG plus MD squared. IO equal to IG plus MD squared. Now, because this test, it gives you radius of gyration or R. So you use MK squared plus MR squared. So then the rest is work. So work, you look at free body diagram only. So the spring do work. Spring do work. Spring do work or not? Yes, Moment also do work. Weight do work or not? Oh, this one don't do work. So right. Okay, only spring do work and couple moment do work. Okay, so you cancel. You can find the value, substitute the value. Okay, the value. You want to find the angular velocity after you move. So it was central G move 0.8. It tell you this one, this body move this one, move 0.8. So they must be a distant rotate. So this rotation or this radius must be moved at a certain 0.8, 0.18. So you should be able to find the distance traveled or angular, how many angle you must rotate to get 0.18 meter. Okay. Okay. So again, if you are using S equal to R theta, you are given that it was moved 0.18 meter. You have the radius, you should be able to find how many angle, how many radian it is already rotate to travel 0.18. Okay. So you need to rotate 0.72 radian to move 0.8. This object move 0.8. Okay. So once you have the radian, you're able to find the missing parameter. Okay. So once you find the angle, you should be able to find distance traveled by the spring. Because here you find the angle already, you should be able to find the distance traveled by the spring. Okay, then you substitute that. Solve, you're able to find your omega. If this is the vector, so vector have direction. Okay. In this case, your omega is square. So you have a square root. When you square root, you have positive, negative answer. Okay, example 4. I will leave it as your homework. This is civil application. A bit more on, okay, it will be also, you can say as mechanical also can. But this one is your homework. The same application apply. He asks you to determine normal and friction force at the arm here. Okay. So this one, your homework. Plus. Number 3.
That's 2. Why is it 0.72 radian times 0.5? Saying the R is 0.25.
0.72, you multiply by 0.25, what you get? Sometimes it's by 0.18. 1.8. Yeah, there's a mistake in my calculation here. It should not be 0.5. It should be 0.25. Okay, it should be 0.25. Okay, so this answer is wrong. But the step is there. Just need to change this R into 0.5. Before 0.25. Right. Yep. There's a mistake here. There's a mistake here. Number 4, your homework. Okay, example 4, you need to use the previous section. F equal to MA and moment equal to I alpha. Need to use them. So go home and look at example 4. Okay, I go very fast in conservation of energy. Conservation of energy means there's no loss of energy. Energy before equals to energy after. And this one, I need to highlight this one. The work of a conservative force is independent of path and depend on the initial and final position of the body. So this theorem only apply on the force that is independent of the path. Example of this one, go back to the previous chapter when we talk about conservation of energy in particles. Give you some example of this. Okay, now this one, you see this one before. Energy, potential energy, because of the datum, above datum give you positive potential energy, mgh. Below datum, negative. Okay. Elastic potential energy, spring give you potential energy. Just now is kinetic energy. Just now is the spring energy. This one is potential energy because of elastic. So don't confuse with the previous one and this one. So when you want to do conservation energy, you consider the energy, the potential energy before and after, but you need to consider whether got spring or not, spring or the location of datum. Okay. So the complete principle of work energy into conservation of energy is this one, the complete one. The complete principle of work and energy is kinetic plus potential. This is energy before plus the changes of work equal to kinetic energy after. This is the complete one. So non-conservative force is like friction. So in simplified, we use if the question asks you to force you to use conservation of energy, you just need to consider two types of energy, kinetic and potential before equal to kinetic potential after. So I just highlight only problem involving conservative forces can only be solved by this one. If you have non-conservative, you need to use this equation. So, okay, example of non-conservative are here. Okay, so I'll give you example 5. Example 5, your homework, go and see. I need to cover one example in your assignment. This one your homework will be the same. I go fast on examples. Maybe I choose one to discuss, then another one is your homework. Pick this one. Yeah, pick this one as a sample. Okay, now you have this system, you know that this got the spring system, central gravity. This one move in the linear form, transition. So you're given mass, confined, spring stiffness given when stretch 0 degree. Determine angular velocity of rod AB when theta equal to 0. So you have the stretching. If the rod is released from rest at the angle of 30 degree, mean this one 30 degree. So you want to know when you release this, you charge up the spring already. When you release, what is the angular? This one change. This one change. So it's a reverse of that. So what you do, you draw free body diagram. Okay, free body diagram. You put our data, you put our weight there, central quantity. Okay, so displacement will be sine theta, 0.4 sine theta is this one, and this one. So hypotenuse and the opposite is a sine. Okay, so S1 is sine. This distance here is so Y1 is sine. So this is when you charge up at 30 degree or any angle. When you pull this one, your S or your Y1 will be 0.4 sine something, sine theta. So when we reach at your datum, this one, there's only one forces W here, right? And the S is 0 because this is your datum. Right, you back to your datum. Okay. Then you use potential energy. You find the potential energy first. So at position 1, central gravity loaded below datum is your datum below. So your gravity actually is a negative energy, right? So your before loaded, you have negative MGH because of weight is below datum. So negative MGH or WH or WY1 plus the spring already charged up so much. So the potential of the spring is half kx squared. S is this one. Okay, so you substitute all the value. We ask you, we give you how much is stretched at 30 degrees. So just substitute that. Find one potential energy. Then after you reach datum 0 degree. So 0 degree center of gravity reach here. So the S will be 0. MGH will be 0. Your H is 0. Your spring will be stretched. Your spring also back to 0. Okay, your spring equation is this one. When you're at second location, spring S 0. So potential energy for second scenario is 0. Then you put inside kinetic energy. So kinetic energy, you load this one, you release from rest. You load already, release from rest. So V will be V equal to omega R. So before you release, it do not rotate. So do not rotate omega 0. So your V1 is 0, of course, for R. V equal to omega R. So T1 0. Okay, so why T1 0? Because your equation is this one. T equal to half I omega squared. Omega 0. Okay. Then position 2, you have 2. One is mv squared. mv squared and rotation. Ig omega squared. Okay, you substitute value there. Find your T2. So T2, 1 is missing. Where is your V2? So what you do analysis using IC analysis. So you have A and B and the IC point. So this is your velocity of the gravitational point. This is your omega. This is the R. So your V, this one, V2, is I omega. Sorry, R omega. R is 0.2. The length of this length is 0.2. Multiply by the omega, you get your V. Put this one here. The whole equation, you have only one unknown, omega 2. So the T2 will reach this one. You put inside conservation of energy equation. Put inside there, again, you are seeing a square equation. Square root of positive, negative. Okay. So this one, it will rotate clockwise. So the right-hand rules tell you it will be positive direction. So positive 4.825. Okay, example 6, your homework. Go ahead and read. With this, we conclude chapter 7. Okay. Okay, we end our lesson here. Take note on the due date again. Due date, email written now.